This will include a review of basic diesel combustion as it relates to exhaust emissions. Components of the exhaust gas recirculation system will be introduced, and the operation of each component will be discussed. Finally, the effects of exhaust gas recirculation on engine components will also be examined. Simply stated, the exhaust gas recirculation system takes a portion of the exhaust gas and returns it to the combustion chamber. To help understand how this reduces harmful emissions, let's first review some of the principles of diesel combustion. In a diesel engine, combustion occurs when fuel is injected into a cylinder containing air under high pressure and temperature. The rapidly burned fuel releases a large amount of heat energy. The release of heat energy drastically increases the pressure in the cylinder. This increased pressure drives the piston downward. This transfer of heat energy to mechanical energy makes it possible to power a truck, operate a generator, or perform countless other jobs Cummins engines are designed to do. The more oxygen available for combustion, the higher the combustion efficiency. 1 pound of fuel needs approximately 20 pounds of air to burn efficiently. Heat is produced during the compression stroke. As the air in the cylinder is compressed, the air molecules rub against each other, creating friction. Friction raises the temperature of the air to the point that when the fuel is injected into the cylinder, the mixture is ignited and begins to burn. Fuel, the third element necessary for combustion, is comprised almost entirely of combinations of hydrogen and carbon. Fuels differ in their ratio of hydrogen to carbon. These variations are commonly referred to as hydrocarbons. Previous approaches of emission control are not capable of meeting the new requirements. The next viable step in reducing peak combustion temperatures and therefore reducing emissions is to cool some of the exhaust gas, mix it with fresh intake air, and move this mixture into the combustion chamber. This process is known as exhaust gas recirculation, or EGR. The mixture of recirculated exhaust gas and fresh intake air is referred to as the charge air. The extra exhaust gas in the charge air is inert. This means that it has virtually no oxygen in it, therefore it will not support combustion. Also, some of the heat energy during combustion is absorbed by the inert exhaust gas instead of the fresh air, thereby reducing peak combustion temperature. This reduces the formation of NOx while minimizing the use of retarded timing. Pressure inside the exhaust manifold is increased. This is accomplished through the use of a variable geometry turbocharger, an exhaust throttle orifice, or other restrictions. The recirculated exhaust gas enters the water-cooled EGR cooler from the exhaust manifold, where its temperature is reduced. The cooled gas then continues to flow through the exhaust tubing to the EGR valve. When commanded to do so, the EGR valve opens and allows more exhaust gas to flow. The gas then flows through the EGR connection tubing toward the intake air inlet. On the intake side of the engine, the recirculated exhaust gas enters an inlet mixer. At this point, the compressed fresh intake air coming from the turbo is combined with the recirculated exhaust gas to form the charge air for combustion. This charge air then enters the intake manifold and then the combustion cylinders. The sliding nozzle inside of the turbine housing adjusts to vary the turbine volute exit area. This action creates the increased back pressure in the exhaust manifold to force some of the exhaust gas through the EGR valve when it opens. The sliding nozzle is adjusted by the VG actuator. With the nozzle ring fully closed, the turbine volute exit area is at its minimum. This creates the maximum exhaust manifold pressure. Turbocharger shaft speed and boost pressure are at their highest. With the nozzle ring in the fully open position, the turbine volute exit area is at its maximum. This creates the minimum exhaust manifold pressure. Turbocharger shaft speed and boost are at their lowest. The sliding nozzle position is infinitely variable between open and closed. After cleaning the area around the turbocharger actuator, Drain the coolant and disconnect the turbocharger actuator coolant supply and return lines. Disconnect the wiring harness from the turbocharger actuator by sliding the locking tang to the open position, then pushing down on the release lever and pulling the connection apart. Loosen the cap screws holding the actuator to the turbocharger bearing housing. Remove the loosened cap screws and actuator. Use a clean cloth to wipe around the surface where the turbocharger actuator seals to the turbocharger. Note, take care not to drop any dirt or debris into the turbocharger. Inspect the sealing surfaces and the rubber sealing gasket for signs of leaks, cracks, or damage. Inspect the pinion gear on the actuator for seizure, excessive wear, or damaged teeth. Replace the actuator if the pinion gear is seized, teeth worn, or damaged. Inspect the sector gear on the turbocharger for excessive wear, damaged teeth, or a broken shaft. Grasp the sector gear and move it through its operational range. The sector gear must move smoothly through the range of motion. Excessive force should not be required to move the sector gear. Within the turbocharger, there are solid end stops which limit sector gear travel in both directions. To determine this, slide the gear to the compressor housing, align the holes in the sector gear and the turbo housing. This will indicate full travel in that direction. Rotate the sector gear to the turbine housing and half of the alignment hole should appear at the side of the sector gear. If the sector gear does not go through the full range of motion, or the sector gear requires excessive force to move by hand, replace the turbocharger. Grasp the sector gear and rotate the sector gear toward the turbocharger compressor cover until the through hole lines up with the blind hole in the bearing housing. Use the alignment pin included in the service kit to make sure the sector gear is in the correct position prior to actuator installation. Coat the teeth on the sector gear with the grease packet supplied in the installation kit. It is critical for smooth, reliable operation of the actuator to use the full amount of the Cummins supplied grease. Remove the alignment pin. Connect the actuator to the engine harness. Install the new gasket. Connect the batteries. Connect Insight using a designated inline connection. Align the actuator and gasket assembly with the turbocharger bearing housing face with the two lower cap screws. Align the actuator to the bearing housing and slide the actuator into place. The actuator pinion gear and the turbocharger sector gear must engage smoothly. If not, verify that the sector gear through hole and the bearing housing blind hole are aligned. Install the 4 cap screws. Torque to specification. Using Insight, calibrate the actuator. The outwardly opening poppet valve opens into the exhaust manifold and is controlled by a high-speed electric motor. The actuator on the valve signals the ECM the actual position of the EGR valve. The ECM constantly adjusts the valve lift through the use of the motor to produce the necessary gas flow. The EGR actuator is serviceable. To service it, remove the EGR valve assembly. Then remove the cap screws connecting the EGR valve actuator to the assembly. Remove the EGR valve actuator shim if required. Replace the EGR valve actuator shim before installing the new EGR valve actuator. Place the EGR valve actuator on the EGR valve housing. Insert the 4 cap screws and hand tighten them. Torque to specification. Refer to the service procedure for the correct torque specifications. Install the 2 straight-threaded plugs into the coolant and vent ports. Install the plug with the O-ring into the coolant inlet of the EGR cooler using a cap screw. Install the collet and cap over the pipe coupling and coolant outlet. And secure with the provided hose clamp. Connect the pressure regulator to the collet assembly and pressurize the EGR cooler to 30 psi. Submerge the assembly in water in a vertical position and check for air bubbles. Inspect for bubbles escaping from uncapped gas ports of the EGR cooler or from the exterior shell of the cooler. Verify that bubbles are not a result of loose fittings or trapped air. Bubbles coming from a failed EGR cooler may be very small and/or may not be a steady stream. If bubbles are not observed, the EGR cooler is reusable. If the EGR cooler is not reusable, inspect the turbocharger turbine housing for any signs of coolant deposits. As we stated earlier, by cooling the recirculated exhaust gas, the overall temperature of the charge air will be reduced, thereby reducing the peak combustion temperature and reducing NOx formation. The coolant and EGR gases enter the cooler on the same end of the cooler and flow parallel to each other. As the gas enters the cooler, a diffuser ensures even distribution. The even distribution is the only way to achieve the necessary cooling of the gas. As we stated earlier, there is a need to increase the cylinder pressure with EGR to maintain the power levels that were available in equivalent non-EGR engines. This increases the possibility of abrasive wear in the cylinder, as well as additional stress levels on other base engine components. With the possibility of increased wear and stress on engine components, lubrication oil will need to meet new standards. In summary, for combustion to take place, the proper amount of air must be introduced into the combustion chamber. The piston on its upward stroke compresses the air, producing friction between the air molecules, which raises the temperature in the cylinder. At the proper moment, fuel is injected into the cylinder. Compression in the cylinder continues until ignition. At that point, combustion takes place, creating heat energy. A portion of the heat energy is converted to mechanical energy by driving the piston downward.